All right, this is section 6.5, and this is entitled the Central Limit Theorem. And the central limit theorem, when you say central, makes it sound important, and it turns out it is. Okay, let's take a look at the central limit theorem. What it does is it relates the sample means to the population mean. Now, if you happen to look at the previous section, 6.4, we talked a little bit about this. Now we're just going to put it into some detail here. So the central limit theorem relates the sample means to the mean of the population. So here's what we do right here. If a population has a distribution that has mean, mu, and standard deviation, sigma, and here's what we do. All right, so you got a population, the mean is mu, standard deviation, sigma. Now, from that population, take all possible samples of some sample size, n. All right, so you take every possible sample that you can of the same size, n. Now, then those sample means turn out to have a distribution that's normal. Okay, that's like over here. All right, you have a population that has mean mu, and then what you do is you take all possible samples of the same size, and then you compute their means. Well, those means have a normal distribution. So some of the means will be real small, some will be real big, but generally they follow this normal curve, right? And for larger and larger n, now that's sample size. So for the larger and larger sample sizes, you get a distribution that more closely resembles this. So if you just have, say, small sample sizes, you might get a distribution that's kind of like this maybe. But as the sample size increase, you get better accuracy and you get a better normal curve shape. So what we're saying then is this, three things. If you have a population with mean mu, standard deviation sigma, you take all possible samples of the same size, then up here, number one, the mean of all the means is the mean of the population. All right, so you take all those sample means, right? You have all these samples. You find the mean of each sample. So you take all these samples, you find the mean of each one. Then you take the mean of those means, right? You find the average of the averages. Well, that average of the averages turns out to be the average of the entire population. And then the standard deviation of those averages, the standard deviation of those means, is not quite just the standard deviation of the population, but rather the standard deviation of the population divided by the square root of the sample size. And then the third one here is that the sample means follow that normal distribution. And just something to note here, just something to note right down here, just a matter of terminology here. Matter of terminology. All right, when we talk about the standard deviation of these sample means of the x bars, all right, we have all these x bars. When we talk about their standard deviation, we sometimes call it the standard error of the mean. So if you hear that phrase, standard error of the mean, we're just talking about the standard deviation of the means. Sounds like it's about time for an example of this. All right, let's take a look. This is problem number 16 out of our textbook here, 12th edition of Brace and Brace. So let x be a random variable that represents the white blood cell count per cubic millimeter of whole blood. All right, so that's like your white blood cell count. Now, assume that x itself has a distribution that's normal. All right, now we're talking about x, not x bar. So x is your white blood cell count. So white blood cell counts have a distribution that's normal. So that would mean something like this. You know, you take some samples of people and you get a white blood cell count that has that distribution. You know, some people have low white blood cell counts, some people have high white blood cell counts, but essentially you get this normal curve, okay? That's what they're talking about here. Now, so we're assuming that x is normal. We are told that. Assume that x has a distribution that's approximately normal. Okay, I just said that. With mean, okay, I better write this stuff down here. Here's the mean. The mean is 7,500. Let me write it so it's readable. 7,500. And the standard deviation is, where is it? 1,750. All right, so I guess for most people this is what the situation is. White blood cell count is normally distributed amongst the population with a mean of 7,500 and a standard deviation of 1750. Now it goes on to say that if you have you get a blood test and if you get a white blood cell count less than 3,500, that is an indication of leukopenia. This indicates a bone marrow depression that may result in viral infection. Okay, so anyway, if your white blood cell count is less than 3,500, maybe it's a problem. Okay, now part A. Let's see if we can do part A here. Part A says, what is the probability that on a single test, X is less than 3,500? Okay, so what I want here is this. What is the probability? I'm just going to write exactly what they said up here. What's the probability on a single test, so sample size of 1, that X is less than 3,500? Now, because X is normal, all right, so I can use z-scores on this, or I can use a calculator. I'm going to do them both here just to remind us how to do them both. Okay, so first of all, by z-score. Now, that means I want this. The probability, okay, I'm just going to write the X again, that X is less than 3,500. Okay, now what I'm going to do is I'm going to convert to Z using this formula, X minus mu over sigma. Okay, so I'm going to get the probability now that Z is less than, okay, X, which is 3,500, minus mu, which is, what was the mu here? 7,500. Boy, oh boy, I'm not doing a good job of writing here. Over sigma, which is 1750. Okay, so we'll make that computation. Now, just be a little bit careful here. We've got to be careful how we put that in the calculator. Here's how I'll put it in. So I'm looking at this. I get a parentheses because I got a fraction here. I got a fraction, and the top of the fraction has an operation. So I'm going to use parentheses to capture all of it and get the order of operations going. So I'll use parentheses. I'll type in 3,500 minus 7,500. Then I'll close the parentheses right above the 7, right above the 8 and the 9. Then I'll press the divide key, and then I'll put in that 1750. I'll press enter, and here's what I get. I'll do it right up here. Z is now less than negative 2.2857 ... But the table, well, we're just going to round off to 2 decimal places. So here's what I get. I get Z is less than negative 2.2. Okay, now I'm going to round off to 2 places. So I look over here. It's an 8. Now, all right, so I want 8. Look at, oh, God. So I just have to be a little bit careful how I put this into the calculator. So I see what I have as a fraction. All right, I got a fraction, a top and a bottom, and the top has an operation in it. So I'm going to use parentheses to capture that whole top. So I'm going to put in like this, parentheses, left parentheses, right above the 8. 3,500 minus 7,500, close the parentheses right above the 9, press the divide key, and type in 1750. All right, now when I did that, here's what I got. So I'll do it right up here. This is now the probability that Z is less than, now here's what my calculator shows, negative 2.2857, 2857, ... and so on. But I'm going to round this off to just 2 decimal places. So what am I going to look at here? 2 decimal places right here. So I'm going to look at the third. It's a 5. And statistical rounding, we know you round to an even digit. So I'm going to round to the 8. All right, so this is going to be the probability now that Z is less than negative 2.28. And because we're doing this by z-scores, I got to use a table. So I just got a little screenshot of part of the table. So what do we have here? I need negative 2.28. So I come down to the negative 2.2 right here. and then I go over to the 8 column. Now the 8 column, it happens to go like this: negative 2.20, 1, 2, 3, 4, 5, 6, 7, 8. I just lost track. 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so I'm getting 0.0113. 0.0113. And let me summarize it right here. This says the probability that some person goes in, gets a blood test, and X, that person's white blood cell count comes out to be less than 3,500. The probability of that happening is 0.0113. All right, so just to get a feel for this, how likely is that? All right, so 0.0113, if I make it a percentage, it's about 1.1% chance that that's going to happen. Or you could say this: out of the entire population of everybody, say, what proportion of people are going to have white blood cell counts lower than 3,500? About 1.1%. Now, look, that was clearly a tedious way of doing this problem by table, right? It took a long time, lots of places we can go wrong. So how about if we do it and all other problems with the calculator? On our TI-84s, here's what we're going to go for. We're going to go for normal CDF of, now the lower limit, remember this is like negative infinity, and here's how we did that one. It was E negative 99 up to upper limit is 3,500. The mean is 7,500. And the standard deviation was 1750. Okay, there we go. Press enter. Now when I press enter, I'm getting 0.011126 ... If I go to 4 decimal places, I'm looking at this. 0.0111. Okay, I'm going to claim that that's it. Now, when we did this by table, right, when we did it with z-scores in the table, I think we got 0.113. So what's the difference? Well, it turns out this is more accurate because we rounded off. And when you use those tables, you're rounding off to a couple of decimal places. So this is rounded. This is more accurate. It's faster. It's more accurate. Now, just as a reminder, where did all this stuff come from? If you remember, that's great. You can just speed it up and go to the next part of the problem, but I'll go through how we got that. So here's what we do. You want to get that normal CDF, so you press second, VARS, and right above VARS, that's distribution. And here's a picture of our calculator. So you're going to press second, over to VARS. Okay, now I don't count this as a row, so I'm just going to go row 1, row 2, row 3, column 4, right? Row 3, column 4, you find VARS and distribution right above it. All right, so you press second VARS, and what comes up are all your distributions. So now you're going to press, you're going to select number 2, and number 2 is normal CDF, and you get a parentheses. So select that one. Then what comes up is lower. Now the lower, you know, what we're doing is we're going to less than 3,500. So that really goes out to negative infinity. Now here's how we get negative infinity on the calculator. We're going to press second. All right, so what are we going to do here? We're going to press second. Then we're going to press this key here. All right, so what we've done is we press second, and now we're going to come to here, right above the comma, which is right above the 7. So you go to the comma. So we're on the second, the comma, and you can't really see it too well up here, but it's an EE key. The key says EE. I'll write it up here. It says EE. Right? It's like it puts things into scientific notation, exponential form. But when you press that, all right, so now you press that EE key, All right, so E, but it's really the comma. But what you get is just one single E, all right? So you're going to get an E. Now, you want negative infinity. So you type the negative sign. Now, be careful here. You want the negative sign. So the negative sign is, okay, I'm over here on the calculator. I want negative. It's right here. Don't be typing this one, the minus sign. You'll get an error. You want the negative sign. So you're gonna press that key. That gives you the negative sign. So you get the negative, and then you press N99. So what you're typing in is like times 10 to the negative 99, okay, in scientific notation. All right, so what your lower looks like is this. The lower looks like this. E negative 90, that didn't show up too well. E negative 99. Press enter. Go for the upper. Now our upper bound is 3,500. Right? 3,500, we want up to 3,500. Now I've got the 3,500 in. Now you need the mean. All right, so now it's asking you for mu, which is 7,500. Press enter. It's asking you for sigma, which is 1,750, and then you paste. All right, so just put the cursor on paste and press enter. And then what you got is this. You can't see it all, right? So when you actually do it all, you get, here's what it should be, normal CDF of, okay, is E negative 99, 3,500, 7,500, 1,750, and then you press enter, and you get 0.0111 and a bunch of other stuff. Okay, now it looks longer than it really is, because after you do the calculator a few times, you'll get it. Now on to part B. Suppose a doctor uses the average x bar now, of two tests. All right, so now n is equal to 2. All right, we're going to take 2 tests instead of just 1. All right, now what we want to know is, what can we say about the probability distribution of x bar? Okay, now here's what we know. This is what the central limit theorem is all about, that x bar is normal. Now, it doesn't matter what x is, okay? So just as an aside, it does not matter what shape x itself has. X bar is always normal, okay? All right, so I know I can use a normal distribution. Now in part A, I use the normal distribution, but only because we were told up here, assume x is a distribution that's normal. So we were told it's normal. If we weren't told that, we could not use the method we did. All right, but now we're computing about the mean, and the means by the central limit theorem are normal. Okay, so now what I want to know is, what's the probability that still x bar is less than 3,500? All right, so now I want this. What's the probability that x bar is less than 3,500? Okay, let's go directly to the calculator. So on your calculator, here's what you want. You want normal, C, D, F. And how do you get it? Second, Vers number 2. All right, now, what is the lower bound? Negative infinity, and that's E negative 99, right? Second, EE right above the comma, and then negative, not minus, but negative 99. Upper limit, 3,500. The mean, 7,500. And the standard deviation. Now be careful here. Remember, we're dealing with x bar. Central limit theorem that says that the mean of the means is equal to the mean of the population. That's why we are able to use that number. But it also says sigma, the standard deviation of those means, is the actual standard deviation divided by the square root of the sample size. So we need to incorporate this up here. All right, so let's do that. So we're going to type in the 1750, press the divide key, and then press second square, x squared. You get the square root. Now type in a 2, and at least on my calculator, I need to actually arrow that out, get it away from the 2. Then I'll hit the parentheses. Got it? Okay, now press enter. On my calculator, I got this. I got 6.136 ... e negative 4. Now, this e, that's scientific notation. It's 6.136 times 10 to the negative 4. Now, this is scientific notation. So, in scientific notation, I look at what I've got up here. I move the decimal point. Scientific notation just moved the decimal points around. So where did I move it? I moved it 4 places, but now this was negative. So I know I moved it to the right. I moved, to get this number in scientific notation, I must have moved it 4 places to the right. To get it out, I'll go 4 places to the left. So there's 1. I need 3 decimal places. So it's going to be, how about this? 0.1236. Okay, that's 4 decimal places. That's probably enough. All right, so what I'm going to conclude then is that the probability that x bar is less than 3,500, that's equal to about 0.0006. Okay, so what does that mean? That means it's about a 0.06% chance that's going to happen. Or, if you like, you could say it this way: tenths, hundredths, thousandths, 10,000ths. How often would you see this? This being 2 tests giving you an average of less than 3,500 white blood cell count. You would see that maybe 6 out of every 10,000 times.